So linear algebra is a really cool course because you get to really get your first taste of doing pure mathematics, which is not worrying so much about solving individual cases of something or solving for particular answers, but we really get to start asking these big brain questions of, is this true all the time? Is this not true? What are these giant spaces that this lives in? What shape does a solution form? Which is like solving a billion different equations all at once. If you do it generally, then it doesn't really matter what's happening in the small term. You can figure out like the bigger picture in the long term. And so this is kind of some cool stuff. And as such, since we just covered a video on one-to-one and onto functions, I thought it'd be fun to just kind of go through kind of a mental exercise of looking at some connections between being a one-to-one transformation and a little bit of theory. So the question that I want to pose to you in this video is, what does, or rather, so if t is a linear transformation, okay, my question is, what solutions could t of x equals 0 have? Okay, what could this have? And this is a very, I'm just positing the question without any kind of big picture awareness now, but by the end of this video, you will very clearly see why I've asked this question. Okay, so we're going to assume, that of course T is defined by some matrix, and so the image is given by, we take a vector x and we map it to some vector ax. T, of course, a linear transformation, so T going from Rn to Rm. Great. So, what solutions does this have? So the idea being that, remember that we're going to have this matrix A. And this matrix A in and of itself consists of a bunch of vectors. And just for the sake of example, let's just say it consists of 3 vectors with 3 rows. So let's just, for the sake of practice, let's just say this is a 3 by 3 matrix. Okay, but we have 3 vectors. And answering the question t of x equals 0 is the same thing as we take that matrix A, we multiply it by x, which consists of our x1, x2, x3, and we ask ourselves, do we want this to equal the 0 vector? And so this example that I'm giving just goes from R3 to R3, but we want this to happen. And so what could the solutions be? And the answer is that it kind of depends on what the solution could be. So if I call this vector here v1, and I call this v2, and I call this v3, right, that vector there, remember that the vector equation of this thing is x1 times v1 plus x2 times v2 plus x3 times v3. So plus x3 times v3, x3 times v3. And we want to know, does this equal the 0 vector? For some x1, x2, and x3, is there a solution? Now, here's the thing, right? So hopefully some of this theory is going to start kicking in. If these vectors, right, if the columns of A are linearly independent, then what is the solution to this question that I'm asking, right? So if these columns are linearly independent, can x1 and x2 and x3 be any random set of numbers? Like, will there be a solution to this? And the answer is no, right? So if these are linearly independent, the only solution is that x itself is the 0 vector, okay? Now, that means that x1, x2, and x3 are the 0 vector, because by definition, the idea is that if these are linearly independent, that means the only way that we could combine them to get 0 is that this, and this are all just the zero number. And if that's like a little weird, I could take this equation and rewrite it as x1 v1 plus x2 v2 is equal to negative x3 v3. And if you want, you could just relabel that as a new coefficient. But the idea of this is, asking this question, does this set of vectors, can we add them up in some way to get the zero vector, is the same thing as asking, can I combine two of these vectors to give me some multiple of the third one, which is basically saying, hey, is one of these three vectors a linear combination of the first two? But if they're linearly independent, that cannot happen. So the only solution for this is x equals 0. Okay, cool. So what else does that tell us? Well, let's suppose, what if they aren't linearly independent, right? That's a fair thing to say. So if they aren't, so if v1, v2, and v3, if these three vectors are not linearly independent, aka they are linearly dependent, then there could be more than just the trivial solution. Right? More than just the trivial solution. Right? The trivial solution is always an answer. Always has to be. So a solution to this, like putting in the zero vector for x always has to be a solution, because you're asking to take all of these column vectors, you're putting some coefficients in front of them and asking when do they equal 0. But if they're linearly dependent, that means that in theory, there is at least one collection of x1, x2, and x3 that if I add them together, I will get the zero vector. And again, the reason is because I can rewrite it like this, and I could ask, what combination of the first two give me the third vector? And there is going to be a solution. There's going to be some x1, x2, and x3 that do this. So then there could be more than just a trivial solution. So what does that mean in terms of our transformations? So this one here basically says pictorially, it says, we're in our domain, our Rn, we're mapping over to Rm, okay, by some transformation T. And the idea is that if they're linearly dependent, that means there's some vector x1, there's maybe some vector x2, there's the zero vector, right? And over here in our Rm space, there's the zero vector for Rm. So in my example, of course, we were mapping from R3 to R3, but in general, we go from Rn to Rm. And the idea is that we know that our transformation definitely maps the zero vector to the zero vector. That one's always going to happen. But if it's linearly dependent, we could have something like this, right? And what does that mean for us in terms of whether this is one-to-one or not? Well, then, if they are linearly dependent, if these columns are dependent, we immediately get that this is not a one-to-one transformation, right? We have two inputs going to one output, or if we think about it in the proper terms of the definition, it's that every output to be one-to-one can come from at most one input. Right, that's the idea. It could come from no inputs, but it can come from at most one, and this one's coming from 2. So this means if we are linearly dependent, then this is not one-to-one. Not one-to-one, okay? And if the columns are linearly independent, then what this means is that, T of x equals 0 has only the trivial solution. And it turns out that this is enough to prove that then T is one-to-one. One-to-one. So if you are interested in the proof of why that is, you can check out page 105. It's page 105 of the text. And they go through that proof, and I'm happy to talk about it and write about it because I like doing pure math as well. But you'll see it's referenced in theorem 11 and theorem 12 very quickly, and they have like nice little proofs for both of these. But the purpose of this video was just, again, another way of really thinking about theory. We're not working with any concrete transformations. I didn't give you a box of numbers, I didn't give you some matrix A. I didn't give you any specific spaces down here. I just said, look, if we have a linear transformation, what does solving this equation, T of x equals 0, this nice homogeneous equation, what does that tell us? And it turns out, that if we can solve it and get some non-trivial solution, that means these columns are linearly dependent. That means, therefore, that T is not one-to-one, and it turns out that then this matrix will not be invertible. That's something we'll cover in the future. And then it turns out that if we try and solve this, and there's only one solution, and it's the trivial solution. So in other words, we're solving AX equals 0. And if all we get here is that the only solution is the 0 vector, and that's it, like that's the only possible solution, then it turns out that T is one-to-one. It turns out that then all of these columns here are going to be linearly independent. And those are some good things to kind of be able to kind of play back and forth with. So, we've come a long way looking from just systems of equations, and now we're really trying to dive into this theory about how to look at a matrix, how to view these columns as little vectors, and really talking about all the combinations of them and what implications, solving something as simple as this homogeneous matrix equation, like how, the effect that can have, kind of trickles down. It's something so simple, solving one small thing, but it can trickle down in some really big ways. So starting in next week's videos, you're going to see that. You're going to be introduced to this thing called the invertible matrix theorem that's going to have like 13 different statements that are all true. And that list is going to grow. And so this is kind of your first taste of really just using some basic logic and just kind of writing some things down and keeping things general and not doing any like exact examples and really getting some big powerful results. So hopefully you thought that was pretty cool. If so, great. If not, oh well. And I'll catch you all next week.